Hey, Pre-Algebra, welcome back to Online Learning with Miss Gutierrez. Today we're going to start with lesson 98. I hope you guys are doing well. I really still miss you. Wish we could be in class together. Looking forward to our next Zoom meeting. It was so great to see y'all's faces last week. So I know that it'll go well again. I really hope so many of you can still log on and we can still have that time together to answer questions. So just a little reminder, make sure you are saving up those questions, okay? So when you're doing your homework, when you're watching these videos, if anything I say doesn't make sense, if anything you're working on, you're struggling with, not able to get to the right answer, or you look at the answers and you and your parents are like, I have no idea how they got that, please hang on to those questions and ask me, okay? I'd love to answer those questions in our time together. And chances are, if you had that question, at least somebody else in the class did too. So I love when you ask me those questions. So hang on to those if you have them so that we can walk through that stuff together. It makes it even harder with us not being together in person once a week, but we can still get on here and do it just like we did last week. So that, and I thought that worked great. So still very thankful for this option and for the time being. So today we're going to jump right in with scale and scale factor. Okay, so scale is actually talking about like how like a ratio of how a model of something relates to the actual item. Okay, so I've drawn a little baby expo marker on here. Isn't he so cute? Which, by the way, I got new markers and I'm like super excited. I know, I don't know if it's like, well, I'm kind of always excited about new markers, but the whole quarantine thing might be taking my excitement to a whole new level. I don't know. I used one of my essential shopping trips to go get these, so serious stuff. So you can see though that the expo marker I drew on the board is not the same size as my actual expo marker. So let's just kind of do a quick comparison. If I hold it right up against it, you can see that they do look about to be, the smaller one looks to be about half the size of the bigger one. So I actually did measure this out when I drew them so that I could in fact make it exactly half. So let's look at what that means and then how we can represent that by writing a ratio, okay? So for the actual marker, I can measure it. Now I'm using my protractor just because I can, because it's small enough for me to use it. But if you had a ruler, that would totally work too. I can measure it and it shows that it's about 4 3/4 inches long, which is about 4.75 inches long. And then if I measure my little one that I drew here, it measures, or I tried to get it as close as possible to measure to approximately 2.375 inches long, which is exactly half of 4.75. So my ratio of my model here is going to be 1 to my actual, which I could just hold here, which is 2. Okay? So that means that my small one is half the size of my big one. So I could also write that ratio as 1 over 2. So the 1 referring to my model, and then the 2 referring to my object. Okay, so if I know that's my ratio, then I can also use that a ratio or a scale to apply it to something else, okay? So think about this, for example. This was just a super tiny level of illustrating this, but let's talk about like a house, okay? So if I were to draw a picture of my house on here, here's my front door. Here's my garage door. It's like a little roof thing here. There's a big roof up here. There's like a window here and all these things. There's like a big like thing here. I don't know. Okay, that's basically what my house looks like. So if I were to draw my house and I were to say like, okay, on this picture, this distance down here is approximately 6 inches, okay? Or which is also half a foot. So it might make more sense for me to write that as 0.5 feet. So half a foot, okay? Now if the actual length of my house, and I'm just like really roughly estimating here, but if the actual like length across the front of my house is, let's say 20 feet, okay? So this would be my model representing the actual object of my actual house would have a bottom base of 20 feet. So if that's the case, half of a foot versus 20 feet, well, we don't really want to make a fraction that involves a decimal like that. So what we can do is we can say, okay, well, I could just multiply both of these by 2 because half times 2 or 0.5 times 2 gives me 1. So bear with me here. You're not really going to have to do this part, but I'm just doing this for the sake of showing you what it's going to look like, okay? 20 times 2, which is 40. Okay, so my ratio of this scale right here to my actual house would be 1 to 40. That doesn't really seem accurate, but you get the idea. Okay, so if that were the case, and I knew that this side right here measured about 0.75 feet, okay? Then I could set up my model to object of 1 over 40 and make a proportion where that's equal to my actual measure. So this would be my scale measure. This would be my actual measure. Okay, and I've got an actual model measurement of 0.75 here over my unknown object. So then to find my actual height, I could just cross multiply. Okay, so we're just setting up proportions here, and we're going to use a little table just like this to do that. So let's look at some other examples. This was just kind of my rough, like, let me just kind of show you kind of thing. But we can look at example 1 in the book that says a model airplane is built with a scale of 1 to 24. If the wingspan of the model is 18 inches, the wingspan of the actual airplane is how many feet? Okay, so we want to do the same thing we just did. We've got the model and then we've got the object, okay? And we are gonna set those up as scale and then actual measure. So they give us the scale here. They tell us the scale is 1 to 24. So when they say that, the model is generally always the smaller one and the object is generally the bigger one. Not always, because sometimes this could be backwards and we could be talking about something microscopic, okay? So we could be drawing a picture of it bigger than it actually is. But generally for what we're gonna be looking at here, the object itself is the bigger one. So we'll set it up as 1 to 24 and they'll always mention it respectively, so you'll be able to tell. So 1 to 24, and then they give us an actual measurement of the model saying that that is 18 inches. So we want to know how long is the object itself, okay? So, and the question says the wingspan of the actual airplane is how many feet? So keep that in mind. We are looking for feet here. So that means that we are not going to be done after we cross multiply. We're still going to have to do a unit conversion, okay? So just keep that in the back of your mind and always keep eyes out for those different units, okay? Like if you're given part of your question in inches and then the other part is asking for feet, okay? That should always signal a red flag in your brain, like, oh, I'm going to have to do a conversion, okay? So always, always, always be watching for that. Okay, you guys are smart. I know you got that. Okay, so let's look at this. We want to cross multiply. So I'm going to multiply 18 times 24, which would give us, did they actually multiply it? I don't think they actually multiplied it because they said that they know once they multiply that, they're still going to have to turn it into feet. So to turn inches into feet, we always divide by 12. Okay, so they said, I know if I'm going to, oh, they did actually multiply it there. They did 432. Oh, well, okay, we'll just finish it this way. Because you could also cross simplify. You could say, all right, I know those can both be divided by 12. So this would be 1, this would be 2. So then you're really just multiplying 18 by 2 here, which would give you 36 feet. And that's it. All right, so let's try another one. Okay, and actually if you look on page 676, it shows you a graphical representation of what it would look like if you plotted the points. And it actually forms a line, meaning there's a linear representation there between the model and the corresponding actual lengths, okay? And that might not make a whole lot of sense unless you're looking at it, but go ahead and you can look at that graph if it helps you. So we're gonna look at example 2. Okay, so example 2 says Sophia is molding a model of a car from clay. The scale of the model is 1 to 36. If the height of the car is 4 feet 6 inches, what should be the height of the model in inches? So we're going to do the same thing. We're going to set up our table. We know model to object. And then we've got our scale and our actual measurement. Okay. So we are told that the scale is 1 to 36. Okay, we know the model is smaller because we're talking about an actual car versus a little clay car. Okay, so the model that she's making is little, so it's going to represent the 1. Okay, and then we are told that the car is 4 feet 6 inches tall. Okay, so let's talk about this for a second, because the question is asking what should be the height of the model in inches. So we want this, the model. We want this to be inches, okay? If we are given feet and inches, we have to do something with this. We can't keep it in both feet and inches. We have to either turn it into just feet or turn it into just inches. Well, we know we're going towards inches anyway. We might as well just turn this into inches. So you can do that by saying, I know that 4 feet, there is actually 12 inches in a foot. So if each of these 4 feet have 12 inches, that's going to be a total of 48 inches. Plus those extra 6 inches right there makes a total of 54 inches. This is the value that I want to plug in here to use. Okay, so now I can cross multiply, which would give me, this is what I don't know. So this would give me 36x equals 54, okay? Because 36 times x, 36x. 1 times 54 is 54. I want to get x by itself and figure out what that is. So I got to divide by 36, okay? 54 cannot be divided evenly by 36. It can, however, be reduced, and it can be turned into a mixed number. So now there's a couple different ways to do that. I think most of you prefer the division method like we talked about last week. So you can do 54 divided by 36. Well, that goes in 1 time. 1 times 36 is 36. We subtract. That would give us 8. And we borrowed. That would give us 1. So we've got 18 left over. So we're talking about 1 and 18 over 36. Can we still reduce 18 over 36? Yes, we can. Good job. So 18 over 36, both of those can be divided by 18. So we are going to divide by 18 there and get 1 and 1 over 2. Okay, you guys are doing great. Hang in there. We're almost done. There's an example 3. It's very similar. It kind of just goes over the same process, but how you can look at it just a tiny bit differently. I'm actually not really going to look at that one today. This is a long lesson, so I'm going to skip that one for now. We're going to move on to example 4, because I do want you to see how this pertains to similar triangles, because we've talked about that recently. So let's look at some similar triangles. If we've got this guy here, who has sides 12, 16, and 20. Okay, and then we've got this here with sides 15, 20, and 25. Okay, now if we are told that these are similar triangles, remember we said this little squiggly means similar, just one squiggly. Okay, similar triangles, okay? So if we want to calculate the scale factor from the smaller triangle to the larger triangle, okay? So that means that whatever this smaller triangle is multiplied by, it's gonna be multiplied by some scale factor to give us these measurements over here, because that's how scale factor works. You take the smaller triangle, you multiply each one of those measurements by the scale factor, and it gives you these bigger measurements, okay? We don't know what that scale factor is, but we do know all of these measurements and all these measurements. So really all we have to do, if we already know these are similar figures, is you can pick one set of corresponding sides. You don't have to do this with all of them. You just pick one, okay? I might pick 16 and 20. You might want to pick 12 and 15. Guess what? We would get the same answer. If you want to try that, you do 12 and 15 while I do 16 and 20, and let's see if we end up in the same place, okay? So there's your challenge. If you want to do that, go ahead and do that right now. But I'll show you how to do it. So I'm going to use 16 and 20. I'm going to say 16 times some scale factor that I don't know yet is going to equal 20. Well, if I wanted to figure out what this scale factor actually is, all I have to do is get it by itself. I have to solve for it. So I'm going to divide. I'm going to do the opposite of multiplying by 16, which is to divide by 16. And I'm going to divide by 16 on both sides. So 20 divided by 16 cannot divide evenly, but it can reduce. So both of those I know can be divided by 4, and that would give me a 5/4. So then my scale factor is in fact 5/4. And I guarantee you, if you had done 12 and 15 at the same time that I was doing 16 and 20, we would have got to the same place. And if you actually did, then you can see how that works. So awesome, good job. Let's look at, okay, the only other thing they talk about here is like three-dimensional shapes. So let me get rid of this real quick. So the only other thing that we're looking at, they give us like volume and, do they talk about, I don't think they talk about surface area. Yeah, so volume of this, yeah, the scale factor. Okay, let's just look at example. Sorry, we'll look at example 5. So example 5 says the smaller of two similar rectangular prisms has dimensions of 2 by 3 by 4. The larger has dimensions of 6 by 9 by 12. What is the scale factor from the smaller to the larger rectangular prism is the first question. Okay, so let me just kind of sketch these out real quick, just so that we kind of have a rough idea. So we've got 2, 3, 4, okay, and then we've got, don't judge my drawings, I know they're not the best thing ever. I'm doing my best with what I got here. You guys get the idea. 6, 9, and 12. Okay, so we want to know the scale factor from the smaller to the larger. So again, we could do the exact same thing. We could say, okay, corresponding sides. You can pick any of them. It doesn't matter. I'm going to pick 3 to 9, okay? So going from 3 to 9, I know that 3 times some scale factor equals 9. I don't know what that scale factor is yet, but I know how to find it because I know that 3 times the scale factor equals 9. So to reverse that process and figure out the scale factor, I just have to do the opposite, which is to divide. So that leaves me with just my scale factor. 9 divided by 3 is going to give me 3. So if I check that, 2 times 3 is 6. 4 times 3 is 12. So that's consistent. So that would be my answer to part A. Okay. Now to keep going, I'm going to have to erase that though. Part B says the area of any face of the larger prism is how many times the area of the corresponding face of the smaller prism. Okay, so let's test this out. So in part B, we're talking about area. Okay, so let's look at, it says any face. So I'm going to pick one. Let's pick this one. So this face compared to this face. So the area of that gives me a rectangle, right? So area of a rectangle is always, what is it? Oh, I know all of you said it. Length times width. Yep, good. Length times width. So that's going to be 2 times 3. Okay. So then, which would actually give me 6. So the area here is 6. On this one, same thing. Area is length times width. So my length and my width on this one are going to be 6 and 9. So 6 times 9 equals 54. So now to find the scale factor of my areas, I'm saying from the smaller to the larger, 6, an area of 6 times what equals 54? Well, we can work backwards just like we did before. We can say to get scale factor by itself, I divide, I do the opposite, which 54 divided by 6 is 9. Okay, so our scale factor from side to side, let's kind of keep a track up here. So side to side, our scale factor was 3. Area to area, our scale factor was 9. So now we're going to look at, you guessed it, volume. So let me see if I can just get rid of this stuff real quick. All right, so the third part asks the volume of the larger solid is how many times the volume of the smaller solid. So volume is always length times width times height when we're talking about a rectangular prism like this. Or like last week, we talked about how it's area of the base times the height, okay? In a rectangular prism, we're allowed to say length times width times height, okay? But I want you to keep in mind, like we did last week, that area of the base times the height, okay? So we can look at 2 times, oops, I said 2 and I wrote 3. This is getting to be too long of a video, sorry guys. 2 times 3 times 4, 6 times 9 times 12. Okay, so we multiply all that out. This one is gonna give us 24. Remember, we could say centimeters cubed. And then this one is gonna give us 648 centimeters cubed. So same thing, 24 times what equals 648? Well, to figure that out, we know we can divide just like we have been doing on all the other ones, and that is gonna give us 27. So now again, this was for the volumes. So my volume scale factor from volume to volume was 27. Now I want you to notice something here, okay? When we calculate area, our units are always squared, right? So if I square 3, that gives me 9. So area, the area to area can just mean you square the scale factor, the side to side scale factor. Okay, because 3 squared is 9. If you notice, my volume units, just like we looked at here, are always cubed, which means to multiply a measurement times itself, right? So if I start at my side to side measurement again, scale factor again, 3 times 3 times 3, 3 times 3 is 9, 9 times 3 is 27. So this volume to volume is actually the cubed version of my side to side scale factor. Y'all see that relationship? I hope that makes sense. It's a lot easier to do this when we're in person, I feel like, because we can be a little bit more hands-on with this, but I know you guys are gonna do great, and I know you can always look back if you have questions at the examples in the book, and you can always rewatch this if you are like, oh my gosh, that was kind of a lot. Go back and rewatch it. You totally can do it. Watch just pieces of it. I know this one ended up being a little long. There was a lot in this lesson. But you are going to get a little break on the next lesson from me because I actually am just going to send you a YouTube video that I like for teaching Pythagorean theorem. So you guys just have to watch that one. It's not me talking. It's not me on the whiteboard. I know you're disappointed. Sorry. But I'll be back for lesson 100. Happy homework, guys.